Hello everyone, thank you for watching this video. I'm Meiyi from the University of Virginia. I'm very glad to present our paper SaSTL, Spatial Aggregation Signal Temporal for Runtime Monitoring in Smart Cities. So people are developing smart cities all around the world by putting sensors in the city to collect city data, developing smart services to improve cities' safety and performance. For example, Smart London in UK or the Area of Things in Chicago, and so on. So for these smart services and city platform, monitoring city states in real time to ensure safety and performance requirements is very important. For example, a navigation app on our phone monitors the traffic volume. When there is a traffic congestion, it redirects vehicle to another road. Where happen to be a park, it raises the air pollution nearby. This changing of states could affect people's health and should be monitored at runtime by the air quality service or city center. An example requirement could be, say, the worst air quality index within 500 meters of a park should always be better than moderate. And by this way, if a requirement violation is detected, the city operators and smart service can take actions to change the states, such as improving the traffic performance, rejecting unsafe actions, or sending alarms to people, and so on. However, building a runtime monitor is very challenging. First, the requirements are specified in English. How can we use an expressive, machine-understandable language to specify city requirements? And also, in smart cities, one requirement could be involved with the data of thousands of sensors aggregated from different locations. And traditional specification language can only monitor a single trace on temporal domain. How to efficiently monitor requirements with multiple sensor data streams is another big challenge. So to deal with these challenges, this work made the following contributions. It's the first work to study 1,000 real city requirements and determine what is really needed for specifying city requirements. And based on the study, we developed a novel specification language, SaSTL. And more importantly, is the first work to apply STL variants to very large-scale problems and running in real time. We also built novel efficient monitoring algorithms. And from the evaluation, we can see that SaSTL has a much higher coverage expressiveness. It reaches 95% evaluated on real city requirements. And we perform large-scale evaluation on real city data and simulated New York City. And one requirement could involve with 10,000 sensors in one requirement. And the result turned out that our SaSTL monitor can help improve cities' performance. Let's see how SaSTL runtime monitoring works for smart cities. So this framework would operate in a city's control center, and we first formalize a set of city requirements to machine checkable SaSTL formulas. And for city data, different data streams such as air quality emission or noise level is over temporal and spatial domains can be viewed as a three-dimensional matrix. For any signal S in signal domain, each row is a time series data at one location, and each column is a set of data streams from all locations at one time. And next, the efficient real-time monitor for SaSTL verifies the states with the formulas, the requirements, and then returns the Boolean satisfaction to the decision makers who would take actions to resolve the violation. And to support decision making in real time, we improve the efficiency of the monitoring algorithm. So first, to identify the gap of expressing smart city requirements with existing formal specification language, we collected and studied 1,000 real city requirements. That's such as city codes or laws across different application domains, including energy, environment, transportation, emergency, and public safety. And these requirements are from like large cities like New York City, San Francisco, or Chicago, and so on. Some examples of these requirements are highlighted in this table. And we can see that as these highlighted by different colors, that we identify these key elements such as this temporal or spatial or aggregation or condition or comparison. So let's look at one requirement. For example, the first one is says limits the vehicle idling to 1 minute, and this is a temporal. And then it says to any schools, including like pre-K or to 12th grade. This is the aggregation spatial elements, and also say the city of New York is also another spatial requirements. So also we found that this spatial and aggregation are two very important features that almost exist in all the requirements. Let's see here, we highlighted some spatial aggregation ones. Let's take a further look at the spatial aggregation properties in smart cities. So the first important feature is that the locations and point of interest, such as say schools or hospital, and we want to define requirements that specifically for this type of locations. And then second thing is the spatial range. For example, within 500 meters or from 2 to 3 kilometers, that the air quality within this range should satisfy some requirement. And more importantly is the aggregation, because we don't want to check the property at one single location. The requirement always specifies something like all locations, or say the average emission within 500 meters, or the counting operation like 90% of roads should say have no congestions. And if only use STL, we can only specify the requirements for one single location. And if we want to specify this kind of requirements, we have to write one requirement for each single location. And more importantly, we cannot specify the aggregation requirements using STL only. So to deal with that, we first abstract the city spatial domain into a graph with all locations as the set of nodes and the direct connection between them as the edge. Then we use this passé to select the node with certain property, for example, a school or a park. And then we define the spatial domain D that selects all the locations within D1 to D2 and also satisfy passé. For example, we can say here from 0 to D2 is a spatial range. And Also, we can specify a spatial range like a donut shape from, say, D1 to D2. And in a special case that we want to check, say, all the locations within a city as a default range, we can say from 0 to infinity. So here are the formal definition of the syntax and semantics for SaSTL. And in our work, we define two novel and very important operators, the spatial aggregation operator and counting operator. I will explain all these operators in the following slides. So let's first look at this aggregation operator. It evaluates the aggregated product of traces over a set of locations. Basically, it first calculates the sum or average or max or minimal value within a range and then compare it with the requirement. For example, let's look at the right figure. If we want to specify a requirement, so say for this park, within 500 meters, the average air quality should always be less than 100. And this is how we specify it, use the aggregation operator. And next, let's look at the counting operator, that it counts the satisfaction of traces over a set of locations. So for example, in this figure, we have this node that's within 500 meters of this park. Then we will first check if this node satisfies these requirements, this AQI less than 50. And then we count how many nodes satisfy the requirement, like the sum, or we count the average, mean what's the percentage of nodes satisfy the requirement. Say in this example, we want to get the average, mean the percentage of nodes that satisfy the requirement should be larger than 50, like 0.5. And using this counting operator, we can derive another two operators. First one is everywhere. And this everywhere operator basically is that when the mean of this counting operation is larger than 0, that means within this range that all the nodes should satisfy these requirements. And the second one, we can derive a somewhere operator. That's when, also for the counting operator, when the max value that is larger than 0, then we can, that also means that at least one node within this range should satisfy 5. And here is another example that somewhere within this 1,000 meters of this park, the noise level should be less than 50 dB. With this spatial aggregation and counting operators, we can easily specify and verify city requirements in a way that none of the previous specification languages can. So as we've seen from the previous examples, there could be a very large number of data streams to be checked in one single requirement. And the traditional monitoring algorithm checks all locations from the leaves of the syntax tree, which means that it will always check all the locations on the map sequentially first, and even it's not a park. And this is very time consuming and even impossible to calculate for a large scale problem like smart city. So we developed two algorithms to speed up the monitoring, including a cost function. It measures how complex it is to monitor a particular SaSTL formula, and then establishes the order in which the sub-formulas should be evaluated. And then we compute the spatial sub-formulas in parallel. In the evaluation, we first conduct a coverage analysis with 1,000 real city requirements and compare it with other STL and its variants existing specification languages. And then we have two case studies. One is on the runtime monitoring in Chicago, and second one is a runtime conflict detection and resolution among smart services in a simulated New York City. So here is the maps and the overview of the two case studies. So on the map, the nodes, colorful nodes indicates the location of sensors and point of interest, like a school or park or theaters. And in the Chicago case, we use real sensor data from the Area of Things project. And in the New York case, in our simulation, we deploy like 10,000 sensor nodes, and it covers like different application domain like environment, transportation, and so on. You can see we cover a very large range of different variables. We compare the coverage on 1,000 real city requirements between SaSTL and some existing specification languages. Here, the coverage means checking if a requirement can be expressed by a specification logic. And we measured how many of the 1,000 requirements can be specified by each of these four logics. And look at this figure. X-axis is the number of requirements, and y-axis include four specification languages. And we can see that SaSTL has a much higher coverage than the others. It can specify 950 requirements out of 1,000, while SaSTL can only cover 43% and STL covers 18%. So let's look at some examples from the results of runtime monitoring in Chicago. First, this is a requirement on the air quality within 5 kilometers of all parks, and this should be always above moderate in 3 hours. And we check these requirements at different time duration during the day and calculate the percentage of satisfaction. So from the results, we can see that the satisfaction rate is very low during 11 a.m. to 2 p.m. on workdays, and so is 7 a.m. to 10 a.m. on workdays too. So how can these results be helpful? A message for the city decision makers from this result could be they should take actions to reduce the air pollution near the park during that time. And also for the citizens, they can learn that they shouldn't take a walk at the park around noon and weekdays. A second case is that we have a requirement on safety, say for the blocks with a high crime rate. The average light level within 3 kilometers should always be high. And we check the satisfaction rate of these requirements, and we can see that still on workdays from say 4 p.m. to 11 p.m. this satisfaction rate is very low. And based on these results, for the city decision makers, they really should increase the illumination of critical areas in the evening to keep people safe. And also the citizens should avoid these areas in the evening. So we can see that these results are very helpful for these city decision makers to make decisions both like offline or for this online real-time decision making. And in the second case study, we did a runtime conflict detection and resolution in a simulated New York City. And to do that, we first implemented 10 smart services running in this city. And these services will monitor city states and take actions. Then at the city operating center, our solution checks the requested actions and detect if there is a potential conflict by runtime monitoring the changing of city states with the requested actions. And we run this simulation for a month, and over this time we compare the average performance of the city when there is no monitor or there is a STL monitor or using this SaSTL monitor. And from the results, we can see that our solution can significantly reduce the number of violations and improve cities' performance regarding the air quality, noise level, and also the safety critical requirements like the emergency vehicle waiting time, and so on. Then we also check that which requirements are most likely to be violated at runtime, and also which service are most likely conflicting with others. And for example, here this R1 checks the average noise level in school areas are violated mostly in this simulation. And also this accident service and emergency service conflicting with other services a lot. So with these results, the city decision makers can think about if they should refine this requirement if it's too strict, or what actions they can take to ensure the operation of these important services. And next, we compare the performance on the computing time. And to do that, we check these 80 requirements, and we compare the number of requirements can be checked on different counting time. Say, for example, if we use this traditional monitoring algorithm, half of the requirements will be checked over 2 minutes, and this even for a very long time. But when we use this optimized efficient algorithm with this parallel computing, and when there is 8 threads, we can see that all the requirements can be checked within 2 minutes. And this is very important to ensure the runtime monitoring in the city. So some insights from this work. Our work is the first to apply this STL variants to a very large scale problem, and it's built on real city requirements. And I think we have moved the methodology towards real cities. And it has more value, a broad value can be used by city decision makers or service designers or even city planners and everyday citizens. It could be used in real time or for this offline checking. And that's all. Thank you for watching my presentation on our paper SaSTL. And please let me know if you have any questions, and feel free to leave your comments or send me an email directly. I would be very glad to discuss this work with you.